Recording in progress.
All right, let's get started with the lecture. So far, we have covered the introduction. We have discussed the partition function, and we on the chapter of state functions. Excuse me, do you have a question or should we discuss something together? Please don't hesitate to formulate any open questions. Otherwise, I would appreciate the silence. We did discover how to write the energy in terms of a partition function. We discussed pressure as another example, which you just arrived again for the question. And then we had a revisit of work and heat, since these are some of the most important applications of classical thermodynamics at the introductory level. Today, I'd like to enter the topic of entropy, which is truly a fascinating concept. It was established only relatively late in classical thermodynamics. And of course, people were eager to look at entropy from the statistical mechanics point of view. Let's begin by making some observations. And I'm giving these letters to walk through the subchapter. So these are like subsections, if you wish. You will have encountered in daily life that water evaporates or, given the outside temperature, sublimates spontaneously. Now, the process of such a phase change implies that intermolecular binding is broken. And a purely enthalpic view on these processes would not be in favor of this to happen. In other words, the evaporization consumes energy, which is why the environment is being cooled down as water evaporates, hence the cooling effect of cooling devices that use vapor. Now, the force that's driving that process is what we call the entropy. And the great breakthrough of the free energies was to combine enthalpy with entropy. So enthalpy or energy being as old as the Hamiltonian principle on Newton, and entropy being much more recent. This was properly put on rigorous footing by Gibbs only in the 19th century at Yale. And hence the name, the Gibbs energy. So this is an observation. Water evaporates, and this leads to cooling. So entropy can clearly, obviously, play a decisive role in the direction of chemical reaction and processes. Anybody arguing against that would argue against daily observations. Another famous example as an experiment, you can easily imagine where you have two containers and they are separated by a wall, and one contains the gas of one substance and the other one of another substance. If you remove the wall, between the two containers, you will observe spontaneous mixing. I should put attention that I don't forget about one of these symbols, but and that happens for temperature, the and volume being fixed and in complete isolation. So something is happening, but we are not doing anything to it, right? Again, no energy change, right? But we clearly observe a process here. So these observations and many more, of course, clearly establish the need for entropy. Now, to introduce entropy at the microscopic level, we need to talk about disorder, okay? So from these observations and from classical considerations before, it seemed clear that entropy has to do something with disorder. Now, it's important to distinguish disorder from chaos. This is not chaos. Okay. You can think maybe of disorder like something unordered, right? Lack of order, lack of homogeneity. And there's a mathematical definition for this. So this disorder, let's define it for the symbol W, capital W. And I apologize, we do not have enough letters, neither in Latin nor in Greek, other languages. So sometimes we need to use the same letter for different purposes. So W also is being used for work, but here we use the capital version for disorder. And disorder can be defined as the number of possibilities to generate the same macrostate. So number of microscopic possibilities, right? Let's insert microscopic here. This is akin to saying that the same distribution over accessible microstates This number of possibility hence corresponds to the ratio of A combinatorial, right? A being the number of members in the ensemble, if you remember, over the product of our microstates populations. So recall that the sum over Aj is the total capital A, right? And it's this ratio, right, of all the possible combinations divided by the product of possible occupation numbers. So, in other words, you have the sum over Aj factorial over the product of the population numbers factorial. So this is maybe a bit abstract. Let's consider two examples. Somebody has a coin here. Anybody, please? Volunteers? Yes. Fantastic. You have one. I don't need money. Thank you. If you would be so kind to throw it up in the air and tell me if you have head or tail. Tails. Come again? Tails. Tail. And now once more, please. Heads. Heads. Now once more. Tails again. Tails again. Thank you. That is sufficient. We have here for these 3 coins, for these having thrown the coin 3 times, our total number of the possible populations, right, is 3. And we have, in this case, if we say that A1 corresponds to number of heads, that's the population number of the head state, right? And A2 is the number of tails. Then when you sum these 2 up and you throw 3 times, you must get 3, right? So our capital A is 3, and our number of states is 2, right? Head or tail. And the particular macro state your colleague just generated, right, corresponds to TTH, 2 times tail, 1 times H, okay? Now the disorder is our A factorial over the product, right? So for this macro state W over the product is 3 factorial over 2 factorial over 1 factorial, which is 3. Okay. So this is what the formula says. Now let's see if this truly corresponds to the number of possible ways to generate this state. I could also generate the same state by having a T here and doing an H here, right? It's a different ordering, right? But the different ordering happens at the micro level. The macro state doesn't care. It's just counting, right? And I could, of course, also go up here. I threw, your colleague threw the coin 3 times. So I could have first head and then twice tail. Right? There's no other way I could generate that same macro state. There's only 3, not more, not less. Could I generate other macro states? What about HHT? Same thing, just flip the indices. You also have 3. Same formula. What about TTT? One would be the number of heads would be 0. My A2 would be 3. I put it in my formula and I have W 3 factorial, 0 factorial, and 3 factorial. 0 factorial is 1. So I have 3 factorial divided by 3 factorial is 1. There's only one way I can generate the macro state TTT, right? And conversely, of course, for head, head, head. Another famous example, this example 1. Or another example that is frequently encountered in combinatorics is throwing dice. Imagine somebody gave you 60 dice. Okay. Now, the number of possible states in the coin flip is just head and tail. And the dice, you have the 6 faces of the cube, right? So NS equals 6. Now, if we assume that by coincidence, every face on the dice is not only equally probable, but also when you realize the experiment, also is observed as frequently as every other face, right? That would mean that out of the 60 dice, 10 should end up on the same face. And so our disorder for that macro state is 60 divided, and the product of all the micro states population numbers, which are always the same, is then 10 factorial to the 6. You have these 6 faces, right? And so that corresponds to roughly 10 to the 42. Now, if I consider a different macro state, namely that all the 60 dice, when you throw them, they always fall onto the same face. So A1 gets populated 60 times, and A2 equals A3 equals A6 equals 0, then my disorder is 60 factorial divided by 60 factorial is 1. And if I consider something less extreme, let's say 55 times I observed one phase, 5 times another one, and none the others, my disorder is 60 factorial, 55 factorial, 5 factorial, 10 to the 6. I can draw a figure where I plot my W versus my A, the A's I have, and my A can either be 0, or at most, if all microstates are empty except for one, it can reach capital A. Okay. And then I can ask how these populations result in different W's. And in particular, if all your A's correspond to the average, then you would have this case of 10 to the 42. So something extremely high. And so the probability that you're out here is 1. And the probability that you're up here is 10 to the 42. It's 10 to the 42 times more likely to have an A distribution close to the average. Right? In other words, if you throw a die 60 times and it falls 60 times on the same face, that's extremely, that's a freak event that is hardly going to happen. But the probability is, of course, very small. Now, we can ask this question, what happens as you vary the number of dices? Right? So this is for A equals 60. Now, if you take only one die and you throw it, then each phase is equally likely. Each macro state equals that microstate. So for that, the W should be flat, right? It's 1. If you have 2 dice, it looks like this, right? So you throw 2 dice, the largest number of ways to generate a macro state would be obtained for the macro state 7, right? And as you add more dice, becomes more and more a normal distribution. Are there any questions on this little excursion into combinatorics? Yes, please.
What is A for every value that's not the average? So if A was 50, for example, what would that actually be for the rest of the dice?
The capital A or the small? So if A, okay, this would be, yeah, it's sort of a measure of the distribution of these states, right?
Okay.
So if all your A's are on the average, right, that would be the case where everything is 10, 10, 10, 10, 10, right? Then as you move outward, you're shifting the distribution. So this macro state, right, which is this combination of microstates, gets shifted outward, right? So it's this small a is like a collective A, right? Yeah. Which is why I dropped the index, right? It's not the state specific one. Yeah. Very good point. Yeah. Okay. So let's look at how this can relate then to the entropy. Right. So dear old good Ludwig Boltzmann again. This was his second strike. And very similar in spirit to the partition function and the Boltzmann factor, said, well, my entropy is some function of this W we just discussed. Okay. And the challenge is, what is F? Okay. Now, from classical thermodynamics, we knew already that dg dt is related to the entropy. Now, G is extensive. T is not, which would mean that S is extensive. Okay. That means if I have two systems, A and B, my S should be divisible simply by addition. Okay. But we know that the disorder of things, right, is multiplicative. And so this means the W, the total, right? The total S tot and W tot should look like this. Now, which function does this? That's right, the logarithm, right? So S has to do with the logarithm of W, right? Because I can then apply the logarithm laws and I get my sum of my two entropies, right? And in order to scale things properly, we slap the Boltzmann constant in front of it. We've encountered this already. So that gives us the right units. So in some sense, this logarithm of the disorder is just scaling your Boltzmann constant. The Boltzmann constant carries the units. We know from classical thermodynamics that to get to the free energy, to my energy, right, I still need to multiply entropy by temperature. So the units should be joules per Kelvin. Right? And that's also, of course, consistent with the Boltzmann factor. Right? And we have beta. And now we can insert our expression for the disorder. Again, I'm using the logarithm rules. And I now make use of an approximation known as Stirling's formula, which says that for large n, so the limit of n going to infinity, my logarithm of n factorial becomes n times logarithm n minus n. Okay? That's really useful to get rid of this pesky factorial. And if I insert this here, my entropy now becomes KB times A logarithm A minus A. And now the same with the population numbers. And I can actually, let me rewrite this term. Because of the logarithm rules, I can pull the product symbol in front of the whole thing. So I would have the sum over logarithms of aj factorial, right? So I have the sum now of a logarithm a plus the sum of a. So these are again summing over j, right? Now you recall that the sum over my population numbers is capital A, and that cancels exactly with my A here. So I have KB capital A logarithm capital A minus sum over AJ logarithm AJ. Sorry, and my okay. Now, as we know from classical thermodynamics, the tendency of the entropy is to grow in the process, right? So processes happen, entropic processes happen because entropy is growing. So we can consider what would drive S upward, right? And that is quite straightforward. So consider how S is growing as W is growing. So the W is maximal, right? If all the A's are the same. So W is maximal for complete degeneracy. Right? In terms of energy, every state is equally likely. Right? It's the same probability of each state. Right? So if that is given, right, chances are these states are all the same. And AI equals AJ equals until ANS equals the average. What happens then? Then the sum over AJ is simply NS times the average. And we know still that this is capital A. So NS times the average is your capital A. Right? And so what happens to the entropy if that's the case? S becomes KB, and now I replace my capital A by NS A bar, logarithm, and then A is again NS A bar. minus ns a bar logarithm a bar. I can factor out my ns n bar, a bar, and I have the logarithm of ns plus the logarithm of a bar. That's this term here, minus the logarithm of a bar. Excuse me? Right. Now, these terms annihilate each other, and I'm left with KB NSA logarithm of NS. But that's capital A. So that's my system size. And I can divide by the system size to get sort of the equivalent to my molar entropy. And so S divided by A would become S of my system is KB logarithm of NS. So the most entropy you could possibly get is for completely degenerate, for a set of completely degenerate microstates, and your entropy would be directly proportional to the logarithm of the number of those states. Just a final example, because before we can conclude today's lecture, consider n degenerate spin particles. So they have plus 1/2 or minus 1/2, right? For instance, in some transition metal, or in some complex, or also in an extended system, some spin lattice. And this means there are ns equals to states. And the A equals n, and your S becomes KB n logarithm 2, which is roughly 0.7. And so if I divide by n, I can have my molar entropy for R times 0.7, R being 8.31 joules per Kelvin and mole. Okay. We just calculated the entropy contribution for such a system. Now you could imagine you change that number of particles, you change the spin states, because you offer more possibilities to form linear combinations with other fermions. Then you might have more states, and you could easily estimate corresponding changes in entropy. Are there any questions? All good. I'd like to thank for your attention, and I'll see you on Thursday.